We are about to start the third week lesson. Today we will talk about really quite like conceptual math stuff, so I hope I will not lose you through the process, but let's see. And also what I will be teaching today is not something that you necessarily have to all kind of remember by heart. It's again kind of just maybe talking about concepts, but just not to stay on like the shallow edge where we are just talking about the concepts but never actually showing anything from the, as an example, I will be showing some like definitions and some mathematical notation today. Okay, so we will start with mathematical notation of something that we saw last class as well. Then we will look into some properties of operators, not operators anyway. And then we will have a pause and then jump to logic. And then sort of as a reward, in the last segment of the class, we will be drawing circles with code. Cool. So when you look at these Cthulhian glyphs, does it like resonate in any way with you? Do you know what these things mean? Okay? No? Maybe? Okay, if you write too many of them, the Dark Lord comes and... no. So this is kind of a lead up into talking about mathematical notation. And so in maths, we often have some like relatively simple thing that we talk about, but we want to talk about it in a very concise way. And so we have these symbols that represent something. So the first symbol here is for all, meaning we will see it later in like an example, but it means sort of like for all possible values for this number, and then we want to say something is true. And the second one means exists. So it's like maybe sometimes in definitions you want to say that there exists a number for which something is true. And so maybe that's the number that you are looking for in some cases. Okay, this is quite like still conceptual. Let's bring it down into something we have seen last class. So let's define something relatively simple. And that is just like looking at a function. What is a global maximum? So think about it. How would you describe to your fellow mathematician friend or fellow friend what is a global maximum? Yeah. Of what? Of a function, maybe? Like given a function, the highest point. What does it mean to be at the highest point? Yeah. Yeah, so it's like for every other value or for every value, maximum point is the one which is larger than every other value, maybe? Would be way how to say it. So sometimes you say it in a little bit more convoluted way, but yeah, I don't know. Yeah, so we get it as a concept, and now how to describe it kind of like in more rigorous way using some mathematical symbology, and later I will also talk about why. Why not just describe it in language? Cool. So, okay. So bear with me. There will be like a lot of notation this class, which maybe is a little bit. Like it doesn't make much sense at start, but like later, all of those concepts are really simple, so we will just go through them. Okay, so a function is this red line, basically. How we write it in maths is like this. So to say, function f is something which translates from numbers you throw in it into numbers that go out of it. And so you could have, the double R means real numbers, so it means that the function is something that will give you values in like real numbers. And this x could also be real numbers. So it can be like, this is a fancy way how to say, hey, this is a function. I throw something in it, something goes out. Cool. This bit means I have a number c, let's call it like a variable c, that goes from the domain of numbers that we can throw into the function. Basically what I said with all of this is, I have a function and I want to have a number that I throw into the function, nothing more. Cool. And so now let's define it. Let C, which is the number from the domain, be the global maximum point of a function, this animal, which is basically a function, if, and now comes the definition, if for all numbers that we could throw in this function, this thing is true, so this one. So value of the function at point C is larger or equal than value of the function at any other number for all the numbers. So there is a lot of text on this screen, so yeah, this point gives larger function value than any of the other values that we can try. If I kind of just erase the stuff that I had to explain, this would be like a definition in some book. So instead of having to define, okay, global maximum is the highest point with a function, function means this, 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 you kind of refer to people knowing what is a function, what is a point, etc. And then you just have this sort of one-line or two-line definition saying the same thing that we were describing. However, it's kind of in a concise way. So let C be the global maximum point. So we call point C global maximum point if it's larger than any other number. That's it. Right. So it's simple, but for some reason we kind of define it with a rigorous way how to write these. Okay, cool. So the concept behind this is that the concept behind having definitions. So in mathematics, we have definitions which are sort of like building blocks. So we have many small bits that we kind of define as individual. This is the most simple element. This is another most simple element. And this is something that is true about those two elements. So we are kind of building brick by brick the definitions, and then slowly from that you make some more complex concepts. So this image, I don't know if you know this painting. Yeah, it's the Babel Tower, or Tower of Babel. And the story is that the humanity has been, it's a biblical story. The humanity has become too proud, and they aim to build a tower which would reach the heaven. And they are actually succeeding, building everything up. So what happens is that the God entity for their pride punishes them by spreading a just confusion of languages in between them. And so with everyone now talking in different languages, no one can actually get together and realize what's up, and they stop the building and it all fails. This project fails. And so this is like slightly connected with the with having a mathematical language, because I mean you can call this in a different way, but these signs, these glyphs, sort of would be understandable in any language. So you can then start talking with Indian mathematicians who would be using the same terminology, the same definitions, the same maths. So that's kind of like the cool idea behind this. Okay, and also it's a way how to write these laws in a relatively concise way. So instead of having a bunch of paragraphs describing what you want to say, you have one small elegant formula, and then you are expecting other people to understand it from that, which is, yeah, cool. So this was kind of the maybe motivation for the start of the class. And now let's talk about operators. What is an operator? So operator is everything that you can see here. So pluses, minuses, times, division. If you have Boolean or like true or false, you can say not. That's an operator. A scene of something is an operator. So it's basically in a formula, if you're writing it down, everything that's connecting to like numbers somehow. And so in this class, we could like, yeah, rather than just like learning how to use plus or something, which would be really simple, and sort of everyone of us knows it already from the high school, let's talk rather about the rules that are behind these operators. Yeah, and so sort of like the properties that they can have. So Again, this is something that is kind of useful, because if you discover that an operator has a property, and we will get into what these properties are, or some examples of them, then you can kind of think about what a complicated formula, how it could be solved, what can you do with that animal, and sometimes you don't even know whatever the operator is, but you know some property of it, and you can use it to solve it somehow, or like make it easier. Cool. So, for example, one of the rules is a priority of evaluation. So we kind of do know that you have to, like, if you have A times B plus C, you have to first evaluate the times, right? That one, and then only at the end add some C. But kind of without some definitions, if no one told you these rules, you wouldn't know. Of course you wouldn't know, because this is something that comes from the rules. Cool. Yeah, simple. There is a basic distinction between two types of operators that I will make now. It's not really that important, but it's just like, yeah, to define something simple and then go into more complicated things. We have binary operations and unary operations. And so the binary ones take 2 inputs and release 1 output, and the unary takes just 1 input and releases 2 outputs. So this image sort of illustrates it, right? We have 2 things here. There is a magical black box, which is, for example, plus, and it will add it together. Yeah? Right, so if A is true, not A would be false. Yeah, like if A is not a real number, but if it's a binary, zeros or ones, then not would be just flipping it back. I mean, you cannot do not a real number. But in programming, it's quite easy, right? It's the same as if like in Python you're writing if something is true, then if... Yeah. So in maths you can also have numbers which are, or like this could also be Boolean. This could be true or false here as well. Cool. And yeah, so this distinction is really like minuscule. It's just if it takes 2 inputs or 1 input. But it will kind of, I'm narrowing it down, and I will talk just about one category of them, which will be, more useful later. So now let's talk about some of the properties, and one of the properties is called associativity. And what does this thing mean? And I will preface both, like, we will talk about 2 properties today, maybe more about like illustrating the point rather than actually needing you to remember these things. But I will always preface it with a human-readable definition. So, associativity means that rearranging the parentheses in the expression with these operators will not change its value. So, this is true for plus, for example. So if you have, I don't know, like, 13 plus 1 plus 2, you can just rearrange these parentheses in any way and it's still true. So you can say, okay, 13 plus parentheses, and like you will throw them here, 1 plus 2, is still the same thing. That's true for plus. So for the operator plus, it is associative. So for example, for times, it's the same as well. So you can say 2 times 3 times, I don't know, 4, and then you can just shuffle the parentheses around, and it's still true. So why does this matter at all? Well, sometimes it's like, it would be easier for you to remember, like, okay, maybe you will have 10 here, and maybe you will have 1/10 here. And so it makes less sense to calculate this first, because you know this can be like erased into 1. So, and this is a simplistic example when we are just like calculating with numbers. But so yeah, this is something that will evaluate really easily into just 1. But if we have some really complicated task where calculating these single steps takes a lot of time, and we discover that there is something which just evaluates into 1, then we have 1, because we have like sped up this one particular computation really a lot. Okay. And so just to make another example of what doesn't work like this, we can say that minus doesn't really work like that. So 3 minus 1 minus 1, which would evaluate into 2 into 1, right? Like just like let's comment it 1. And we would say 3 minus 1 minus 1. This would evaluate into 0, and this would evaluate into 3. And so that's not true, right? It's like 1 is not 3. Cool. So for the operator minus, we know that it's not associative. Cool. So now, this was kind of just showing you how this works, but then there are some slides which will talk about the same thing with some mathematical notations. So similarly, like before, when we had maximum, global maximum is easy to understand. To read it from the formulation is sometimes harder, but let's just go through it anyway. A binary operation, a block, a glyph block, is called associative if for all 3 numbers which come from reals, so for some 3 numbers, this is true. So basically that's what I'm always trying here, right? This is the A, B, C, A, B, C. And this is, instead of the block glyph here, I'm just putting a minus there. And so maybe it's quite difficult to look at it with the block. So if you replace the thing with a star, it's still true. But the star doesn't have to mean multiplication, right? It can be any operator that we are talking about. Cool? So, and how to kind of translate it into human language. If for any 3 numbers from real numbers, we can just willy-nilly swap the brackets like this, then we know it's associative. Nice. So yeah, this is true for multiplication and addition, as I was showing here before, and it's not true for subtraction. Nice. A sort of real-world example is concatenating 2 words together. So we have done this in Python, right? Hello world today. If you concatenate hello world and then add today to it, it's the same as hello world today, and it's the same. So you can extend this into like real world things as well. Nice. So this would be associativity. Yeah, right. And so in Python we have often worked with functions, and so we can have like a function which does something to 2 things. And sometimes we would like to apply that function for like a whole list of things, right? And so if the function itself is associative, we don't really care if we call it like this and then like this, or if we call it like this and then like this. So, and in programming very practically, maybe evaluating this, the left side, is much faster than evaluating the right side. So that's like the reasons behind it. Cool. Now the second out of the 2 properties that I will talk about today is the commutativity. Yeah, in human readable definition, a binary operation, that operation sign is commutative if changing the order of the operands doesn't change the result. It means that if you have, yeah, let's use it with just A and B, some numbers which come from real numbers, so that can be anything, right? A plus B, well, it's the same thing as B plus A, because that's how it works. So this is true for plus, right? We can just shuffle them around and again calculate whatever we want first and then later go to something else. This also is true for multiplication. A times B is the same as B times A. Cool. But again, it would not be true for minus. So if I say A minus B, it's not the same as B minus A, right? Yeah, cool. So that's like a simple case. Yeah, we have the numbers here as well. Yeah, so we kind of do get this human readable formula, right? Just swapping those things changes it or doesn't. That's what makes the operator commutative or not commutative. And here comes the definition. So again, a binary operator, a box, is called commutative if for some 2 numbers which are from real, this is true. So if you have them, AB is the same as BA. Cool. So if we substitute it with something nicer, like a star, then we have something like this. Nice. And so a real-world example, putting on socks resembles a commutative operation, since which sock is put on first is not important. Either way, the result of having both socks on is the same, right? So A is left sock first, B is right sock first, AB is the same as BA. Nice. In contrast, putting on underwear and trousers is not commutative, right? We get that. I don't have to explain that. Okay, good. And the same way, concatenation of two strings is not commutative, because hello world and world hello is not the same. Nice. So this would be commutativity. As a function, if you are like, for some functions we have written in Python, this is true, and for some it's not. So it's like another notation which would talk it as a function. And so we have kind of talked about it in this case. So with addition, we know that addition is associative. We know that addition is also commutative. We know that multiplication is associative and is also commutative. And we have also talked about the example of concatenation. So for association, this is exactly like this rule written out as the example. So T plus E plus, in this case, would mean concatenation of two strings. So T plus E plus A is the same as T plus E plus A. So this is true for this one. So we can swap parentheses around. But the commutativity, hello world and world hello is the same as T plus 8, and yeah, they would not end up in the same as the same animal after this operation. Nice. So, why do we at all care about these properties of these operators? Well, given some of them, we can say something about the operator in general. So, for example, we will know that if we can swap those things around in the formula, we will know if we can change around the parentheses, and this can kind of overall simplify the problem. So I think there was like, by default, these rules were used in maths from like the ancient years. So like, I don't know, the Egyptians have used the basic idea of this, that you can just plus them together and then swap them around. This comes from the like ancient times, sort of. Only in like the 19th century, when math became more systematic, and you kind of, yeah, there was a rise of systematic thinking. So kind of like, okay, we need to have a system, and this system will eventually help us make some more definitions and kind of like think about the math concepts in more abstract way. Only then this rule was kind of, okay, we need these rules, and then it was defined. Yeah. Right. So what is the lesson of this part? I don't really need you to remember what is associativity or what is commutativity. The lesson of this part is that the way how math works, so sort of you are defining even the smallest building blocks. Who really needs to define what is a plus? Like, I mean, we all know what it is, but it is actually useful to have these strange properties, because then they can link to like, okay, if this property is true, this property is true, and this property is true, then this third property or fourth property is true. And if that is true and something, then I can, I don't know, it goes on. Math really builds from these small blocks into like really huge world of abstract laws and definitions. And so sometimes you will open up like a PDF of some mathematician paper or something, and it's madness. It's like these symbols all around. But they come from these like really simple things, and just they are being added together. Yeah. Yeah. So all of this kind of allows like modularity or even redefinition of even the basic steps. So mathematics in theory is not really rigid. You can at any moment say, hey, F8, I don't need plus to be this thing. I will define it as a completely different operator. Or I will define an operator called cube, and this will do these things. So you can kind of define your own math, and then in that math you can create some laws, and then maybe you will discover that it's completely useless. Or maybe you will discover that this particular type of math is useful for solving some problems. Anyway, I was talking about this building from bottom up. Nice. So this is image here. I don't know what is the time now. Right. I will let this sort of sink in. So this is the first pause. We will go into something way more concrete the next part. And we will write some things on the board and on papers. And then we will go into something more like concrete in the sense of coding in the third part. So for now, let's have a pause for like 20 minutes. Okay. All right, guys. Let's continue. So let's continue with the slides. I will start the second part again with a joke from the same comic that I'm sometimes showing. And this one needs some explanation, which is not a good joke usually, but this one is quite good in the end. And also, yeah, there is some message behind that. So, this is a image from Rolle's theorem, which is like a definition that I'll just say is like defined in here. If you have a function which is differentiable, which means it just continues everywhere, there is no hole in it, and yeah, it's not a function, but yeah, if you have a function like this, and some moment you have 2 points for which the function has the same value, this definition says that there must be a point, at least one, in it, where the slope is equal to 0. So basically it says every function like this has to return. Basically, it's not possible for this function to go infinitely there because it has to have returned here. So it's actually like not saying anything complicated, right? It's basically saying every hill has a top, or in theory, every like I don't know valley has a bottom, something. So yeah. So this comic says, every now and then I feel like the math equivalent of the clueless art museum visitor squinting at a painting and saying, come on, my kid could have done that. So basically, that's this. And this is kind of related to, if you know, I don't have a connection here, I think. If you know the pissoir exhibited by Armut, basically it's just a piece which has been taken and like, yeah, even this pissoir is an art. And definitely you could see, like, meet people who are telling you, oh yeah, my kid could have done that, come on, this is not art. But actually it's way more about, like, what the concept behind it is, right? It's way more about, like, maybe extending the boundaries of what is and what is not art, and, yeah, it's, like, quite complicated, right? And so even in this case, it kind of also points that in conceptual maths, there is more to those things, yeah, even if it's, like, a simple one. Anyway, this is, like, a metaphor. Cool. So next we will be talking about like first more practical part for today, and for this one I would like you all to have papers and start writing as well, kind of some tasks we will do together, and it is logic. So far we have been kind of counting with real numbers, so some formula evaluates into some other results and everything. However, from programming, we kind of do know how to operate with booleans, right? We know that we have a variable which is some like true or false, and we know like what not would do with it. We know what and would do with it. We know what or would do with it as well. All of these things. But there is kind of more theoretical way how to think about it, and we will talk about this now. So a single unit of some more complicated formula is called variable. We can think of it as just one bit. So it's either 1 or 0 or true or false, if you prefer. And so how to write it down will be like this, writing a box which says, okay, this is A, and it can be either 0 or 1. Basically, we are like enumerating all the possibilities. And like before, when we had operators such as plus, minus, multiply, etc., which does something with the basic unit, we also have some like unary operators here, and that one is the not operator. So if you have this as your input, the A, and if you do not into it, and this symbol means not, so if you do not A, it will flip it from 0 to 1, from 1 to 0. Right? It's the same as in Python if you would be doing this in programming. Make sense? Okay. What about some other ones? So what about logic AND? So in this case, it's the first binary operator happening between two things. And so to enumerate all the possibilities, we need 4 values here. Basically, in these 4 rows, it's all possibilities that these two could have 0, 0, 0, 1, 1, 0, 1, 1. And so which one of these will be true and which will be false? What will be the numbers kind of here? So like false and false is false. False and true is still false. True and false is still false, and true is the only one which would have 1 here. I think I have it here, yeah. So this is sort of like how we would evaluate AND. Nice. So just like looking at this one operation is simple, right? But like we will start combining them together and making more longer formulas, and then it will make more sense a little bit. Okay? So what do we also know is OR. And that means at least one of the 2 inputs is 1, or both of them are, and then it's true, right? And the more esoteric one is implication. So if you have, it's symbolized by this like arrow. If you have A implies B, it's basically true for, like true implies true, that's good. False can imply anything, and it's still true, which is a little bit confusing. I was confused by this when I was learning about this for the first time. But basically, if the first thing is false, whatever it implies is, it can be both, sort of. It can be like, if from truth, if from false you are implying true, sure, that's good. If from false you are implying false, sure, that's good. Like, both of them are one. Whereas the only one which doesn't work is from truth to imply false. So this one is the only one which is at 0. Right. So it works similarly like these ones. It just has different like places where it's 1 and where it's 0. Okay. I think this is one which we have not met in programming yet, probably. Implication. And then there is last of the simple ones. It's equals, and basically that's, yeah. If both of them two equal, it's 0, 0. It will be truth, right? So you would write this as a if A equals B, then, and this would evaluate into like being true when both of them are the same, and also here when both of them are the same. Nice. So we can kind of draw this out into this larger table. There are few more that we can define. And they are called, they are basically combination of not with other things, and also a kind of adaptation of the OR. So if you have AND, yeah, right. So if you have OR is basically, you can also have exclusive OR, which will be true only in cases where it's, just one of them is true, basically. So XOR, exclusive OR, is the one which kind of evaluates true only in these two cases, right? Okay. Then it's a combination of AND and NOT. So NOT AND is, just to shorten it, NAND, and NOT OR is just to shorten it NOR. And it's the same thing, just you are flipping these evaluations. Nice. And so the first task that we will actually do on paper here, or on board for me, but later it will be on board, is this formula. So, not A or B. So I can also write it with like normal letters, not A or B. And so what do we do with this sort of animal? What do I want to ask you, kind of, is what are all the possible input values, and at the end sort of figure out what is the truth and false for this, right? So very soon, guys, you will have to do this on your own papers, so maybe pay attention. Hello. Cool. So this is something that you will do for like the later tasks yourself, right? Okay, so how we do this is that we have two inputs. We will basically do the same labels as here, A and B. And we will just enumerate all the possibilities that these can have. So A can be false and true, and B can be false, true, or false, or true. So this is just to write out all the options. And somewhere here on the right, I want to get into the state of knowing what this thing is. And so I could do it from hand, probably, like just think really hard and evaluate everything, but way easier is just to like breaking down into smaller bits and go from the smaller bits into evaluating what is the last bit here. So in order to get this, it will probably help me to just look at what the OR values would be here. So A or B, and this one I can remember, so it is 0 for 0 or 0 is 0, right? 0 or 1 is 1, nice. 0 or 1 or 0 is 1, okay, also good. And then 1 or 1 is 1, right? And so in order to get from here to here, it's simple because you can just do the NOT operation to it. So you will do NOT and you will get something like this. Nice. So this sort of setup is the way how we evaluate something more complicated, kind of combined expression from these smaller formulas. So this is still simple. It's like it has 1, 2, 3, 4 words basically in there. It could be a long formula that we don't really know how that evaluates. It can have even like more inputs than just A and B, right? So this one was the one I did on the board, and kind of to show you how to do it. And then this one is something I want you to do it on your own. So take your papers and start evaluating. So basically I want to know these 4 numbers, or this, if there is 1 or 0 in these 4. So this sign here means the equivalent. So if you are lost and kind of don't know which one this sign means, what it means, go back in the slides and look at this this slide where it's like it's this one, the equals row. Yeah. Okay. Okay. So I will now do it on the board. So the easiest, like it's just always figuring out what is the easiest next step to figure out. So in this case, we would like to figure out the not B first, because then we will use it somewhere else, right? So not B is just flipping these. Nice. Then we would like to figure out probably this thing. So A implies not B, and if we just as a note, we can write what the evaluation for A implies B would be. So 0, 0, 1, 1, 1. A 0 implies 0 is 1. 0 implies 1 is 1. 1 implies 0 is the only false. This is the only one you have to kind of take care for in implication, and this one is 1. So we can then look at these in this case, kind of completely forget about B, and we are now doing the A implies not B. So these two buckets, yeah. I mean, most of you have already done it, but still. 0 implies 1 is true. 0 implies 0 is true. 1 implies 1 is 1. 1 implies 0 is the only false. And then what we want as the result is the negative of this. So negative of this animal here. So implies not B. And that's easy, just again flip the version. And so what I was getting at with this question is that the evaluation 0, 0, 0, 1 is the same as you would be getting here in AND. And what it means is basically that this is a more expansive way how to write AND. So in this way we kind of messed it up because we were going the wrong way around, but sometimes you can go from this thing to the easier one. And so maybe somewhere in programming, from the code requirements, you are getting sort of this thing, which is strange, but still. And then you figure it out, oh yeah, but actually it evaluates the same way as AND, so we can just simplify it as AND and have a single thing that you are checking. Yeah. And now, let's do the task number 3, which is this formula. And when you get it, I want you to look at it and see if it's similar to something else that you have seen in this class. Like hint, it probably will be, right? But right, so in this one, the tricky part is probably the implication. So look at the table for implication just to be sure if you are doing it right. And so what I was getting at with this question is that the evaluation 0, 0, 0, 1 is the same as you would be getting here in AND. And what it means is basically that this is a more expansive way how to write AND. So in this way we kind of messed it up because we were going the wrong way around, but sometimes you can go from this thing to the easier one. And so maybe somewhere in programming, from the code requirements, you are getting sort of this thing, which is strange but still, and then you figure it out, oh yeah, but actually it evaluates the same as AND, so you can just simplify it as AND and have a single thing that you are checking. Yeah. Cool. And so let's do the last one, which is this one, task 4. Yeah. 0, 1, 0, 0, yeah. Okay. Does it make sense? Yeah. So I think the trick really is to just not be lazy and really write all the steps, which is I know it's a lot of writing of the same thing, but sometimes it just helps for longer formulas, definitely. So there is a few more interesting things to say about these formulas, and if you paid some attention here, there is the NAND operator, which means not AND, which is basically just flipping AND into whatever the next part is. The thing about NAND is that NAND is all you need, which means that with NAND you can build all the other ones. You can build an AND from just NAND, you can build an OR from just NAND, you can build NOT as well from just NAND. So what this means, let me illustrate on this case. So if you want to do not A, you can write, and not use NOT, but really just use NAND. You can write A NAND A, and in this case we would be looking at 0 NAND 0 evaluates into 1, 0 NAND 0 evaluates again into 1, 1 NAND 1, we are here, evaluates into 0, and then 1 NAND 1 again, we are here, evaluates into 0. But if you look at the inputs here, 0, 0, 1, 1, and then the outputs here, 1, 1, 0, 0, this formula has flipped the AND into the negative. So basically, this thing is the same as saying not A. Right? Which is interesting because what if there was a world where you couldn't use not, but you could have nuns? Yeah. So yeah, I would like to ask you, what is this expression? So that's the task 5 or something now. Just do the same thing like before. Yeah. Yeah, one of the two. Yeah, I don't know. So that's the answer to that. This is AND. Now let's look at the next formulation, and that's this one. A NAND A, NAND B NAND B. Can you evaluate that and tell me what it is? It can be anything. And so we have used NAND to define NOT, to define and to define OR, and basically NAND is all you need. And so this is called NAND logic, where you are just using NAND for everything, and there is a, oh yeah, I don't have connection here for some reason, so I cannot look at this, but there is like a bunch of other conversions here. And so there is also NOR logic, which is the same thing but using not OR, NOR. And for example, the first embedded system, the Apollo guidance computer, was built exclusively from NOR gates. About 5,600 NOR gates in total for later. Yeah. So this means that the Apollo computer, the first one that they sent in or something, just had NOR operators, so some like chips like this, and all of them did just NOR. And they were able to cable it in a way that they are able to just build whatever logic they want, because from NOR you can go to some AND, to some OR, to some NOR, to some XOR. All of them you can build from these basic parts. So it's kind of like saving on the, I don't know, you just need to produce a lot of NANDs or not NORs, and then you can combine everything. Yeah, so that's the kind of message for now. And let's have a pause. And the bit after the pause will be coding again. So let's return to the last bit of today's lecture, and that is again some coding exercise. And this one is kind of following one of the demos we have looked at in the first class, the generative Gestaltung, and in particular this sketch where the code is just simply drawing circles, kind of depending on the mouse position. So there is also some animation because the circle is like wiggling over time, sort of. But let's start with just the simplest step, that is drawing a circle, and let's do it in Python. This is OpenJS. P5.js. Okay, and so to that we kind of really need to figure out what is the maths behind points on circle, and so we will look at the parametric formula of circle. So from the angle, which is going around here, and from the radius, we can get the values x and y. Basically, for changing angle, it will be different values of x and y. And the task will be to write a Python code which would draw a circle, as easy as this. Like there is more advanced version later where we can do some animation with it. And for you, probably the most important message is to use the local PC, because if for this we cannot really use the Colab version, because Colab is not really interactive. We can draw matplotlib there as well, but we cannot like catch the clicks or something. So let's just use your own PCs. And so on our GitHub there are two versions of basically the same code. One is using the matplotlib library, and one is using the tkinter library. And I made two versions because I don't know what is installed on your machines, and just like to try both and see which one works. And both of these first demos, there is everything already. It's on our Git in the week 03. So for example, the tkinter one, there is already the code needed to create a canvas and then kind of to react on click. And then there is a function called draw circle, and there is something that you will kind of, this is the point where you will put all the magic of the mathematical formulas in it. So somewhere here. And I also wrote the draw point function already, so really what you need to do is just change something here in the draw circle. Basically call draw point for every, well, no, not every, but like for some sampling amount of points around the circle. Cool. And so what is the formula? It is kind of given by this sketch where we know that location of x is r times cosinus of the angle, and location of epsilon is the r times sinus of the angle. So you will get these points on this curve, I mean on this circle from this formula with changing angle theta, you would be getting these values here. There is one small detail as well, is that when working with these circles, with these functions, cosinus and sinus, what you need to feed it is radians values, so not from values from 0 to 360, as is the angle kind of like what we would draw it on a board or something, but to go from values of 0 to 2 pi. Yeah, and so this is kind of my hint of, this is the formula to convert whatever the t is from 0 to 360 to the radians. So we multiply it by pi and divide by 180. And then if you feed this thing into these two functions, it is basically just rewriting this formula. It should give you an x and y, the kind of the location that you need to go on a canvas. And so probably what you will need to do in the code is to do this thing, calculate it repeatedly for different t, for like going basically some for cycle which is going from 0 to something, and then you are drawing a point at every iteration of this. So that's the task. A hint is to use math.py, math.cos, math.sin. And if you are all done with that, you can then look into the more advanced version, which is maybe trying to like animate the circles which are being drawn. So for example, you can change the parameter r and kind of have it wobble over time, because you will be increasing it and decreasing it or something. But that's kind of like the second step. Let's first focus on this first one. So open up one of these two demos. Make sure it works on your local PC. As default, it should just show you a canvas where you click, and then it will make a point there where you click. So change that code into drawing a circle code. I kind of recommend you using the second, the Ginter one, because that one is drawing it faster. Like this one is faster as a piece of code. But if you cannot make it run on your PCs, I think matplotlib is easier to set up, to install, because we have also been using it before. So let's just like probably start here and then see if it works, and if it doesn't, just go there.